This is Carolyn Valpy recording Lesson 2 for Education 5400 at Elmira College. Good morning, everyone. It is so wonderful to see you. I hope you're enjoying the warmer weather we've had and that it's given you a chance to get out of the house and get some fresh air. The sun's shining today, so definitely take advantage of that. Summer will be here before you know it. So, the first thing that we're going to talk about today is radioactivity. I know we've been covering radioactivity lately, so let's actually do a little bit of review first. What does radioactivity actually mean? Let's start with, do you remember who first developed a definition of radioactivity? Marie Curie, right. She was working with uranium, and she said that radioactivity refers to emission of rays or particles from certain elements. But there's one really important word that she used in that definition. What was that word? Do you remember? This was in our notes. Spontaneous. Right. For an element to be considered radioactive, it needs to spontaneously emit rays or particles from its nucleus. Now remember, if we were to fire particles or rays at the nucleus of an atom and thereby force the content of that nucleus to change, that's not spontaneous. That's us doing it. So do you remember the term for that process when we force the change? Transmutation. If we are forcing the atom to change, we are performing a transmutation, and it is not spontaneous. But today I'd like to talk about those other reactions, the spontaneous ones. So radioactive elements that spontaneously emit particles or rays from the nucleus, and those particles that they emit could be one of four types. So the first one is alpha particles. Alpha particles, that's the symbol, and it's a helium nucleus with a mass of 4 and a charge of 2. So it has 2 protons and 2 neutrons and a positive 2 charge. When an atom emits an alpha particle, the atomic number will decrease by 2, the atomic number, and the mass number will decrease by 4, because that's what's being taken out of the nucleus of the atom. Remember that both protons and neutrons affect the mass number, while only the protons affect the atomic number. So, the nucleus could also emit beta particles. That's equal to an electron with a -1 charge. So let's look, we have alpha particles, and then there's beta particles. That's the symbol, and it's electron with no mass, meaning the mass is so small that we don't even take it into consideration, and a -1 charge. So a beta particle occurs when one of the neutrons in the nucleus breaks apart to form a positively charged proton and a negatively charged electron or beta particle, which has to get out of the nucleus right away. In the case of beta emission, the mass number will not change because the original neutron and the resulting proton have the same mass, but the atomic number of the atom will increase by 1 because it now has another proton in the nucleus. So similar to beta particles are positrons. So let's look at that. A positron does not have a symbol, but it looks like a beta particle just with a +1, not a -1. So positrons have that +1 charge. They have the same effect as a beta particle, but in a different way. So in the case of positrons, one of the protons in the nucleus, not neutrons, one of the protons breaks apart to form a neutral neutron and a positively charged positron, which has to get out. It gets emitted. So once again, the mass number will not change because the original proton and the resulting neutron have the same mass, but the atomic number will decrease by 1 because that proton became a neutron. So there's 1 fewer protons in the nucleus. Finally, the last one on our chart is gamma rays. It has this symbol. Now, gamma rays are interesting because they have no mass and no charge. But when they're emitted from the nucleus. So they're high energy photons that don't actually change the mass or the atomic number of the atom, but they often accompany the emission of other particles. So let's recap. What are our 4 particles emitted by radioactive nuclei? Alpha particles. Alpha particles, beta particles, positrons, and gamma rays. Very good. So, when we write the equations for radioactive decay of these elements, we need to make sure that the equation is balanced. That means that the charges on both sides of the equation need to be equal, and so do the atomic mass on each side of the arrow. So let's take a look at a couple of examples. This first example talks about alpha particle emission. So we're looking at thorium. Thorium-230, so that is the atomic mass, and this is the atomic number, 90, becomes radium-226 with 88. So 90 is what makes it thorium, 230 is the mass. Radium-88 with 226. So when we write this out, it spontaneously, nothing else over here, spontaneously turns into this because it has emitted an alpha particle. See the helium nucleus with a mass of 4 and a charge of 2, and this gamma ray over here, which just tells us that it's emitted. It's not actually affecting anything. So if we look at the numbers, the atomic number goes from 230 to 226, but it has that 4 from the helium nucleus, whereas the atomic mass goes from 90 to 88, plus that 2 from the alpha particle. Okay. Do you want another example? Let's do another example. How about beta emission this time? So with beta emission, here we've got thorium, and now we're actually going over to protactinium over here. So thorium has the atomic number of 90, whereas protactinium has the atomic number of 91, and thorium's mass number here is 234. So thorium spontaneously emits a beta particle, so it goes from 90 to 91, becoming protactinium, but the beta particle does not take any mass with it. So that means the atomic number goes from 90 to 91, with 90 goes to 91 plus a negative charge, adding a negative charge to it. So 91 plus -1 equals 90, whereas the atomic mass stays the same because the beta particle did not change anything. Excellent. So, when a radioactive element spontaneously emits one or more of these particles or rays, it's called radioactive decay. This process is actually natural for many elements. So how do we know which elements are radioactive? Scientists have found that the more protons and neutrons there are in a nucleus, the less stable the nucleus is. Because protons are positively charged, they should repel each other. Like a magnet, when you put the two sides that are similar together, they push each other apart. Protons should do that, right? But nuclear force, the force that holds those protons together, is stronger than the electromagnetic force, which would push those protons away from each other. So as we add more and more protons, those nuclear forces have a harder time keeping the protons in the nucleus from repelling each other and remaining stable. Beta particles and positrons are emitted by the nucleus when it's trying to achieve a stable state. So, scientists have determined that any element with more than 82 protons in its nucleus is radioactive and subject to radio decay. So, element 82, according to your periodic tables, which are in your reference tables that you will have on the Regents test, any element beyond lead, which is 82, is radioactive. So one thing that we have learned about radioactive decay is that certain element isotopes have what's known as a half-life. A half-life is the time required for 1/2 of the nuclei in the radioisotope sample to decay into products. I think that's an important thing to write down. That's a good definition to know. So let's take a look at that. Definition. Half-life is the time required for 1/2 of the nuclei in the radioisotope sample to decay into products. Meaning half of them will no longer be what you started with. They'll be something else. Everybody got that? Okay, good. So, another way to put that is that during each half-life, half of the remaining radioactive elements decay into atoms of different elements. So you're still going to have the same number of nuclei. They're just not going to be the same nuclei. They're not going to be the same atom in the sample. So half-lives can be incredibly short, like only a matter of seconds, or as long as billions of years. One benefit of radioisotopes with very short half-lives is that they can be used in nuclear medicine because there's very little hazard of long-term radiation effects from gamma rays, which, remember, are emitted during radioactive decay. But there's very short time that those are there, and so there's very little hazard of those radiation effects since the radioactive element is depleted so quickly. So scientists frequently use one of the radioactive isotopes called carbon-14, which is subject to radioactive decay and has a half-life of 5,730 years. That's one that is just really, it's a good one to know because it's so useful. But what I want to point out to you, in your reference sheets, Table N, we will be using Table N today. So, scientists frequently use carbon-14 to find the age of an object by comparing the amount of carbon-14 to the amount of other carbon isotopes in the object. Carbon-14 and the other isotopes will be equal while the object is still alive. But when it dies, all of a sudden, they become different. And those ratios are what help scientists to actually use carbon dating to age things. It has proven very useful to many scientists, especially archaeologists. So you will find the common radioisotope half-lives on Table N of your reference tables. Remember, you will need this to complete your independent work today. So get used to using it because questions will come up on the regents. So now that we know what a half-life is, how do we use it in calculations? Half-life is used in calculations using an exponential decay function. That sounds kind of scary, doesn't it? It's okay. It's not that scary. So here is what it actually says. The amount remaining equals the initial amount you had times 1/2 to the nth exponent, where that exponent n is the number of half-lives. Please note, we don't make it half-lives, it's actually half-lives. So, if we began with an example of, let's say, 24 milligrams of radon-222, let's check this out. 24 milligrams of radon-222, which has a half-life of 3.8 days. So that's a fairly short half-life. The amount remaining after 3.8 days is going to equal 24 milligrams times 1/2 to the what power? To the first power, because it's the first. We're going to make this work. To the first. And so 1/2 to the first is 1/2. 24 times 1/2 is going to be 12 milligrams. 12 milligrams. So after the second half-life, so another 3.8 days, then we're going to have 1/2 to the second. 1/2 to the second is equal to 1/4. So 24 times 1/4 is going to equal 6 milligrams. Oh, we don't need that eraser right now. 6 milligrams. Well, what about another half-life? 11.4 days. So that's 1 half-life, 2 half-lives, 3 half-lives. So amount remaining equals initial amount, 24 milligrams, times 1/2 to the third. What is 1/2 to the third? 1/8. So 24 times 1/8 equals 3 milligrams. Now, looking at these numbers, looking at the numbers that we have here, we had 24 milligrams. Then after one half-life, we went down to 12. Then after another half-life, we went down to 6. Then after another half-life, we went down to 3. So who wants to guess how much we would have after a fourth half-life? Did you guess 1.5? Absolutely. It divides in half each time. So some of you may find it easier to take the original amount and divide it in half, then divide it in half, then divide it in half again. However, when you're working with uneven amounts and lots of half-lives, like hundreds or thousands, then using the equation, this equation, is actually going to be easier. But if the problem is on a small enough scale, you can do the calculations manually. Go for it. If it's easier for you, do that. You can always use this equation to check that your answer is correct. So, let's go through some practice questions. First, let's look at carbon-14. We're looking at carbon-14. So remember, what was carbon-14's half-life? 5,730 years. If you forget, it's on table N. So let's assume that we begin with a mass of 2.00 times 10 to the negative 12th grams of carbon-14. We want to know how much carbon-14 we'll have left at the end of 3 half-lives. Let's plug the information we have into our equation. So we have carbon-14 with a half-life of 5,730 years, and we're starting with a mass of 2.00 times 10 to the negative 12th grams. So the amount remaining equals 2.00 times 10 to the negative 12th. Uh-oh, I made a mistake. Do you guys see what it is? I forgot to put the units. We always want to put our units. Good job. Anyway, so we're going to start with 2.00 times 10 to the negative 12th grams times 1/2 to the third. Now, what is 1/2 to the third power? 1/8. So, now we're going to multiply 2.00 times 10 to the negative 12th grams times 1/8. I'll give you a second to do that on your calculator. Everybody caught up? Okay, that's actually going to give us 0.250 times 10 to the negative 12th grams. Now, is that scientific notation? No, because you got a 0 right here. So let's put that into correct scientific notation. 2.50 times 10 to the negative 13th grams. Excellent job, everybody. Now let's give manganese 56 a try. Manganese 56 has a half-life of 2.6 hours. So if we start with a 1 milligram sample, how much would be left at the end of 10.4 hours? So the first thing we're going to need to do is figure out how many half-lives we're going to go through in 10.4 hours. So let's divide. 10.4 divided by 2.6 equals 4. We're going to have 4 half-lives. So now it's time for our equation. Our amount remaining is equal to our initial amount, which is 1.0 milligrams, times 1/2 to the 4th. So if we multiply that out, what is 1/2 to the 4th? So we have 1.0 milligrams times 1/16. And so that is actually going to equal 0.0625 milligrams. Now, for those of you who actually feel more comfortable dividing several times, let's make sure that these calculations still work out for you. So, we've already determined that 10.4 hours will be 4 half-lives. So let's divide by 2 4 times. 1.0 milligrams divided by 2 equals 0.5 milligrams. 0.5 milligrams divided by 2 equals 0.25 milligrams. That's the second half-life. 0.25 milligrams divided by 2 equals 0.125 milligrams. It's our third half-life. And then 0.125 divided by 2 equals 0.0625 milligrams. That's our fourth half-life. We got the same answer. Awesome. Now let's look at Cobalt 60, but let's take a slightly different approach to this one. Let's assume that we began with a sample of 0.800 grams, and after 10.5 years, we have 0.200 grams. How long is the half-life of Cobalt 60? Well, can we use our equation for this? Let's give it a shot. Cobalt 60, we start with 0.800 grams, and 10.5 years later, we have 0.200 grams. So, let's plug the information we have into our equation. The remaining amount is 0.200 grams, and that's equal to 0.800 grams times 1/2 to the n. We need to find out what n is. That's the number of half-lives. So we'll divide by 0.8 on each side to get rid of it. To get rid of it on that side. Divided by 0.8. Whoops, almost wrote that wrong there. Times 1/2 to the n. So this is going to give us 1/4. And that equals 1/2 to the n. Well, 1/2 squared equals 1/4. So that means that n equals 2. N equals 2. So if n equals 2, how many years did we start with? Up here? 10.5 years. Whoopsie daisies. So 10.5 divided by 2 equals 5.25 years. That is the half-life for Cobalt 60, at least in this example. So next, I want to ask you guys a theoretical question. If thorium-234, and we're not writing this down because I just want you to think about it. If thorium-234 has a half-life of 24.1 days, meaning half of the atoms are going to decay in that time, will all of the thorium-234 atoms decay in 48.2 days, which is twice of the first half-life, which is 24.1? If half of them decayed in 24.1 days, would the other half decay in another 24.1 days? Let's think about that for a second. No, they won't. Because half-life doesn't specify what quantity will decay in that time. It specifies what percent of the sample will decay. Therefore, if thorium-234 loses half of its atoms in 24.1 days, it will only lose half of its remaining atoms in the next 24.1 days. So at the end of 48.2 days, we will still have 1/4 of the number of thorium-234 atoms that we started with. Great job, everybody. Now it's time for some independent practice. So please work on the worksheet that you've been provided in Google Teams. You will need your reference sheet, Table N, for the first part of the assignment. Once you've completed the assignment, please email me a picture and then bring it with you to class tomorrow because we're going to go over it as a class. So just as a recap, today we briefly reviewed transmutation in atomic nuclei, then we moved on to spontaneous radioactive decay. We learned the 4 particles or rays that are emitted by radioactive nuclei: alpha particles, beta particles, gamma rays, and positrons. We learned which elements are radioactive, all of those beyond atomic number 82, and we learned about half-lives and half-life calculations. So tomorrow we're going to do a simulation of radioactive decay to demonstrate half-lives. We can't actually play with radioactive material. The school frowns on that. So you're going to need access to the lab template on Google Teams and 40 coins. Pennies, nickels, dimes, quarters, a mixture, whatever you have. We're going to be gathering our own data from which to draw our own conclusions, and I think you'll be intrigued with the results. Thank you all so much for joining me for this class. I had such a fun time talking through all of this with you. I hope you had fun hearing it. The weather's getting warmer, so go outside and get some fresh air, then come back tomorrow so that we can explore the infinitesimally minute particles that make up the great outdoors. So, have a great day. Bye.